Hi everyone, thanks for joining the session. My name is André Soto and I'll make a deep dive of the DVB-S2 encoder implementation for FPGA, one of the things we've been doing at Phase 4. Firstly, I'd like to thank Michelle W5NYV for all her Phase 4 work, Ron W6RZ for all his amazing new radio work, without which this RTL implementation would have been way harder. I also need to mention Thomas, Anshu and Paul for their contributions and help as well. And before we dive in, let me provide some context by going over essentially 3 questions. What's the scope of the DVB-S2 encoder? How to interact with it? And how does the system looks like? So what is the scope? This is the functional block diagram as it appears in the DVB-S2 spec, and I'm gonna start at the end of this diagram, okay? Here we have the interface to the RF satellite channel. Everything after this point is platform dependent and ultimately depends on the interface to the RF transceivers, so it's out of our scope here. The current implementation starts with the stream adaptation subsystem here, and this effectively delineates the scope. So the current scope includes baseband scrambler, FAC encoding, beep mapping, physical layer framing, and modulation. As of the time of this presentation, there is no padder and no physical layer signaling and pilot insertion, but we do plan to include those as well. The next thing I want to talk about is how to interact with it. The DVB-S2 encoder receives baseband frames at the input and produces modulated physical layer frames at the output. The interfaces we chose here are access stream for both. More on that in a second. The input stream interface carries the configuration for the frame. We have frame length, constellation, and code rate. These 3 make up what I call frame attributes, and they define how the frame should be processed. The remaining parts make up a regular access stream. Okay. The output interface is very similar, but without the frame-based parts. At this point, the data has been modulated, so it's going to have I and Q components essentially. Besides input and output streams, we also have an AXI Lights interface for memory mapped register space access. This register space has 3 main uses that are configuration, status, and debugging. We can configure the bit mapper tables, we can enable and disable dummy frame insertion, and we also need to configure the filter coefficients. Status and debugging are for things like monitoring behavior, controlling the flow of data, and both apply to several internal interfaces. We can, for example, check how many frames in flight we currently have, or what's the biggest, smallest frame that has passed through a certain stage. We can also block a data stream for debug and allow, for example, a word at a time or a frame at a time to check, for example, how the system behaves. The input and output streams timing diagram looks like this. In this example, we can see an input frame configured as short frame, QPSK, encoder rate 1/4. The encoder receives this frame, and at some point in the future, we're gonna see the output frame here. And by the way, this is what I mean when I say frame parameters are constant for a frame during a data transfer. And the last part I want to show on the quick intro topic is how does the system looks like. This is a high-level block diagram of the encoder itself as it's implemented in RTL, and it's very similar to the functional block diagram we've just seen. These red blocks here are instances of the access stream debug, which is the block I mentioned before that allows us to monitor and control the flow of data. A key difference though is the presence of this frame FIFO besides the bit interleaver, and it's used for QPSK frames because QPSK has no bits interleaving. Every block in the system looks similar to this, and most DVB specific stuff will also have frame attributes. But we can't really change them like this, because for example, this green block here has nowhere to get data attributes from. So to support every frame having a different configuration, we need to transport this configuration alongside the frame itself. And we do this by using access stream TID interface. Essentially, STID carries arbitrary data to MTID. In this case, the arbitrary data is the configuration itself, which is encoded. In this gray block, for example, we need frame length, constellation, and code rate. So we decode CID to extract them, and everything just works. We can use this to transport anything that's constant during the frame, and that makes it very simple to connect multiple components. You can see in the top level here, the frame configuration input is encoded into a vector, and that's how it gets transported to other blocks in the design. And this concludes the basics, really. So time to get into the cool stuff, and we're going to start with the baseband scrambler. This is a great first block to look at because it's very straightforward with few design decisions. This is the text of the specification, and the important bits here are: there is an endian as we need to follow, we need a feedback shift register with a certain polynomial, and we need to load this shift register with a certain value whenever a frame starts. The spec also provides a diagram that is actually very close to the RTL implementation. We have a 15-bit shift register, and every time you get a bit at the input, data in this shift register will move from the left to the right. We take bits 14 and 15, add them together to get the new value of bit 1. To get the output bit, we take LFSR bit 1 and XOR/add with the input bit, and then we're ready to get the next bit. Looking at the block diagram, we can see that the baseband scrambler is quite simple. We have the LFSR here that is reset just like I described, and that's going to happen when the design as a whole is reset, or during operation when ST_last is asserted, and that indicates that a frame has completed, so we reset the value to prepare for the next frame. Bit 1 is then XORed with input data, and that will produce the output data. So remember I said there's few design decisions, right? Here I chose to register the ports, but when making this presentation I realized it's actually better to move this to outside and register as needed and leave the baseband scrambler doing only what it is supposed to do. But never mind. Next we have the FAC encoding subsystem, which is made of 3 components: the BCH encoder, LDPC encoder, and the bit interleaver. So BCH encoding takes a baseband frame as an input and appends a parity check to that. The size of this parity check code is given indirectly in the spec. The size is going to depend on the frame length and the code rate. The size of the BB frame is given in the BCH uncoded block column here. And to get the size of the BCH FAC word, we do BCH coded size minus BCH uncoded size. To calculate the actual parity check code, we use a set of polynomials, and then we use frame length and code rates to identify which polynomial index to use. And this index will then identify the polynomial itself. Moving on to the BCH encoder block diagram, and I'll coalesce data streams into a single line from now on. So the internals of the encoder looks like this. The CRC mux does the core CRC calculation, and that's going to include selecting the appropriate polynomial. This block has a constant latency, so to make our life easier, we add this X stream delay to the data stream here at the bottom to make both data and CRC code words arrive at the same time in the output mux. So it's simple to choose which one we want to forward. The CRC mux has no back pressure, which means we only really need to tap off data to it. We don't need to replicate the streams here. Data and parity check code are multiplexed when the input frame completes, and we need a counter to count how many bits the parity check code needs to fit the output data with. The counter essentially helps the shift register here to slice parity check code into data width chunks, if that makes sense. We can look at this by looking at the flow of data, right? So the baseband frame flows to the output and through the CRC mux, and once ST_last is asserted, indicating the input frame completed, we count the number of words needed to shift data from the CRC flip-flop to the output. And by the way, the CRC blocks here are auto-generated. You can find online CRC generators out there. I'll leave a link to the one I used somewhere in the slides. But yeah, any generator should suffice, really. So Moving on to the LDPC encoding. This is the most complex block in the system, okay, and I think it's the most interesting as well. The FAC encoding subsystem receives a baseband frame, adds a BCH FAC code word, and an LDPC FAC code word. The spec gives the size of each one of these blocks in the same table as the BCH stuff we've just seen. The size of the LDPC FAC code word is given by the difference between the LDPC coded block and the LDPC uncoded block. The LDPC encoded block size only depends on the frame size, really, but the size of the LDPC uncoded block, which by the way is the same as the BCH coded block, depends on both frame size and code rate. This is the text for the encoding process as it appears in the spec, but I figured it might be maybe a little too boring if I just read this. So what I'll try to do instead is show you how the process looks like in a minute or so. We start with a data frame. This data frame has a certain length. For this example, it doesn't matter really what the length is, but the spec defines the frame as having k LDPC bits. This frame is then divided in groups of 360 bits each. The parity bits will be stored in a memory, and I'm going to call this the parity memory. Each data bit will be XORed with values pointed by offsets given by the parity bit address table. Essentially, each group of 360 bits will use one row from the parity bit address table like this. So the first bit of the first group will use row 0. And I'm going to put some numbers to help us visualize. Okay. Bit 0 will then be added, that is XORed in offsets 3, 5, 7, and 11. The second bit also uses row 0, but we add Q to the offset. Q is an integer that depends on the frame length and code rate. For this example, let's assume Q equals 3. So for bit 1, the offsets are going to be 3 plus 3, 5 plus 3, 7 plus 3, and 11 plus 3. The third bit is exactly the same as the second bit, except instead of adding Q, we add 2Q. So it's going to map to 3 plus 6 here, and then the others. The remaining bits of this group will use the same process over row 0, incrementing the multiplier of Q each time. The remaining groups will use the same process but using their associate rows, and every time we change rows we reset the Q multiplier to 0. Once all groups are finished, the parity bit memory will be filled with the parity values. For the final step, we consider only this memory. To get the complete LDPC code word, we use a 2-bit sliding window to select the first 2 bits and add them together to get code word bit 0. Next, we slide this window by 1 bit and do the same to get code word bit 1. We repeat this process for the entire parity memory to get the complete code word. This completed code word is then appended to the input frame, and then we are ready to process the next frame. So to understand the implementation, I'm going to divide and conquer. The LDPC encoder is actually made up of 2 subcomponents, the LDPC table and the LDPC core. The LDPC table essentially unrolls the parity bit addresses, which means it deals with selecting the correct base parity bit address table, given the frame length and the code rate. It will track groups of 360 bits, add Q to the offset correctly, and so on. And the LDPC core actually does the parity calculation itself. So let's have a look at the LDPC table first. So first of all, a dedicated module makes testing way simpler and faster. Next, if we go through the DVB spec appendixes B and C, we'll find 21 tables. Each one has a variable number of coefficients, but in total there is almost 6,500 coefficients, and we need 16 bits to represent them. As we've seen previously, we need to unroll the tables, and we need to do that on the fly, because if we start the unrolled values, it would be just way too much data to store internally. Here are 4 examples of how tables actually look like in the spec. These are all for normal frames, but the short frames ones are very similar. So let's zoom in the first one. We can see it has 2 sections. The top one has 12 rows of 15 values, and the bottom one has 30 rows of 3 values. The next one looks very similar. It has 2 sections, 20 by 12 at the top and 12 by 3 at the bottom. The next table is the same pattern, and 2 sections, 36 by 12 at the top and 72 by 3 at the bottom. And in fact, all tables have 2 sections, and the number of rows and columns within each section is constant. And we can use this to our advantage and build a generic table reader that reads the shape of each table from one memory and the actual table data from another memory. And this is going to help with efficient resource usage. So let's have a look at how this works. This is an example of a table. It's small just to keep stuff simple. Okay. What we're going to do is put the table content in one memory and its size in another memory. The tables themselves are always flattened, by the way. And to read this flat memory region, we need to know basically where the table starts, the shape of the top region, and the shape of the bottom region. So let's say the next table looks like this. Again, we split table data from the table size, and like with the previous table, we need to know where this table starts, the shape of the top, and the shape of the bottom section. And we keep doing this for all 21 tables. To actually unroll the table, we also need the value of Q, so we add this to the metadata table. In the end, we have one ROM with all flattened tables stored continuously, and a metadata ROM that tells us how to read this table ROM. In summary, the coefficients ROM has around 100 kilobit worth of data, and it uses 7-block RAM 18 on a Xilinx FPGA. The metadata memory is much smaller, only around 1 kilobit, and it will likely be mapped to lookup tables. So, piecing everything together, frame type and code rate address the metadata table. The metadata table outputs the relevant info to the unroll logic. The unroll logic reads the parity address table to generate offsets for the LDPC core calculation. The unroll logic here is just a bunch of nested counters, so I'm not going to go into details. Timing-wise, a single bit is going to start the process. The LDPC table then generates 1 offset per clock cycle. Besides the coefficients, the LDPC table generates an output called mNext, which marks the end of a row, that is, a new bit can be processed. And this means that this period here, corresponding to offsets 3, 5, 7, and 11, are related to bit 0. Then the following period corresponds to bit 1, then bit 2, and so on. This example shows the outputs for the LDPC in a minute slide. So Q equals 3. And then you can see that when we change from bits 0 to 1, the offset is incremented by Q, and that's going to be true for the second, for the third offsets, and so on. Now let's have a look at how the parity calculation is done in the LDPC core encoder. This is the encoder's block diagram. This block takes data and table inputs. The input data stream is replicated in 2 branches. By the way, replicating means a single stream becomes multiple streams. In this case, it allows both output mux and the input synchronizer blocks to back pressure their inputs, and this back pressure is applied to the data input. So, the branch on the top goes straight to the output, and the other one goes through the input synchronizer and the LDPC accumulation. The accumulation logic uses offsets from the LDPC table to XOR data in the associate positions of the parity RAM. While that's going on, it will keep the output mux selecting data from the axis stream replicate. That's the baseband plus BCH FAC passing through. Once the input frame completes, it will switch to receive data from the post-frame accumulation / with conversion blocks. The frame RAM uses a block RAM internally, and block RAM's data width is naturally 16 bits. Technically 18 bits because ECC, but anyway. That's why we have this width converter from 16 to N, to convert parity data to the output data width. The LDPC input sync is used to synchronize table offsets to data bits. Because parity bit offsets are given 1 per cycle, we need to convert the input data stream to 1 bit as well. This ensures that output data and output offsets are synchronized. Data passes through the width converter directly. Offsets pass through literally directly. Output will be valid when both width converter and table have data. The system is ready to consume data from the width converter when the LDPC table indicates next, and the reader is ready to consume this data as well. We can consume an offset from the LDPC table whenever there's a valid data bit and the reader is ready to consume this data bit as well. The accumulation process is the heart of the LDPC encoding. This block connects directly to the input synchronizer. So here, offsets are used to read the parity RAM. Because each RAM address holds a 16-bit value, we divide this offset by 16. The remainder of the division is used to operate only on the specified bit of the parity RAM read data. We then XOR the input data bit with the specified bit of data from the RAM and write the results back to the RAM itself. Block RAMs have an intrinsic 2-cycle latency between reading an address and data showing up in the read data port. And because we are using the same address for both read and write, we're effectively limited to 1 operation every 3 cycles. So let's change this a little bit. These flip-flops here at the top are used to match the RAM latency. This way we can decouple read and write addresses in time because we don't need to hold read address constant until write data is ready. By the way, we can call this a pipeline now. However, this 2-cycle latency also applies between write data and read data. And this is an issue in cases where we're reading data from an address that's been written less than 2 cycles ago. Write data won't make it in time. This is called a data hazard, and it does happen in some tables in some coefficients. This is solved inside the parity RAM itself by doing some tricks around it. So the actual storage is still a regular block RAM, but we've added some flip-flops responsible for storing pending writes. These are writes that have not yet been committed to the block RAM itself. Read address is still connected to the block RAM, but is also used to check if the address being read is pending, so that read data will always have the most up-to-date data. In other words, read data can be either data from the block RAM or from one of the pending writes. Suppose we are reading and writing from the same address at the same cycle. Write address, write data, and read address will still go to the block RAM. But we can compare the write address and the read address. If they match, we bypass write data. If we're reading from an address written in the previous cycle, we can do the same with data after the first flip-flop. And likewise for reading an address written 2 cycles ago, but with data after the second flip-flop. For anything over 2 cycles, data will just come from the block RAM itself. Unfortunately, this session time is up, even though there is still more to cover. This session only covered baseband scrambler, BCH encoder and LDPC encoder, but there's plenty of interesting blocks still. If there is enough interest, I can cover those in the future. I would like to share the current state of the project though. We have verified all 84 valid configuration combinations in both simulation and in hardware, using GNU Radio results as a baseline. And this includes varying configuration on a per frame basis. We don't need to stop data flow, change parameters, then restart, although there are some caveats. We also have a continuous integration pipeline running on GitHub that runs tests on GNU Radio plus GHDL and some tests with IOSIS. If you're not familiar, GHDL is an open source VHDL simulator, and IOSIS is an open source RTL synthesis suite. We're currently bringing up an over-the-air setup to test against lab equipment in ORI Lab West, located in San Diego, California, and that's the image on the left. Michelle and Paul have been doing an amazing job in the lab. I am trying to get more time to help them out, and I'm sure we can get this setup up and running with lab gear, commercial gear, and that's going to be an incredible milestone. I'm sure there will be some issues. I mean, there's always issues, but we are making progress, and that's great. If this project got you interested and you'd like to get involved, you can check out the GitHub repository, Phase for Ground or Phase for Space websites. Also, if you'd like to get in touch with myself, here are some links as well. By the way, the GitHub user is slightly different than my last name, but it's not a typo. So if you're watching this on Expo 2022, I am now happy to take questions. If not, I will see you next time.